Hi everyone. In this video, we'll continue the discussion of anti-differentiating rational functions. In the past, I suggested that finding a partial fractions decomposition can make it easier to find antiderivatives. But there are also some situations where partial fractions can make things harder. So I want to spend some time here clarifying when you should use partial fractions and also when you shouldn't. Let's look at this rational function, for example. First, notice that it is proper, so should we use partial fractions for this one? Before you go down that route, you should always check whether or not this is already a partial fraction, because if it is, then you would be trying to decompose a partial fraction into partial fractions, which would be a huge waste of your time, as we saw when we first learned about this topic. In this case, the fraction we're looking at is linear over quadratic, but the denominator here is reducible. So for that reason, this is not currently a partial fraction. Pause if necessary to check that the denominator does factor here as x plus 3 all squared, verifying that the denominator is indeed reducible as I claimed. Once we know this is not a partial fraction, we can consider decomposing it into partial fractions, or in other words, finding its PFD. And this will work as far as finding an antiderivative goes, but I'm going to call that our first try, because once we've done this, I actually want to compare it to other potential methods just to help us get a sense of when partial fractions is actually a good idea and when it isn't. Finding the PFD in this case gives you the results that I've just put on your screen. You can pause and verify that for yourself, and I'll also put down the details here to help you with that. But once you're convinced that this is the PFD, what should we do next? Again, pause and think about that if necessary. Well, the correct method now is to perform a substitution where u equals x plus 3. After all, both of these partial fractions are the constant over linear type, and we know those can always be done by just letting u equal the linear function. If you do this, then du equals dx, and so the rest of the details are pretty straightforward. Although again, I encourage you to pause and check all of this. So as you can see, partial fractions get the job done, and it's pretty straightforward, but it's also really tedious to actually go through all the work of finding the values of a and b. So is there another way to do this which is less tedious? Well, in the solution we just used, we ended up making the substitution u equals x plus 3, and when you look at the function we've been given, you might wonder whether this substitution could have been done right at the beginning, avoiding finding partial fractions altogether. So let's try it. If we make this substitution, then du equals dx, which is pretty nice, but you still end up with this pesky x in the numerator. So what can we do with that? Well, that's where we go back to our substitution and figure out what x is equal to. Rearranging that equation shows us that x equals u minus 3 in this case. And so we can sub that in for x to get everything in terms of u. And after that, you could split the fraction into these two terms. Then simplify to end up with a pretty straightforward integral. So after all is said and done, we can get to this answer, which you'll notice is the same one we came up with before, but we managed to avoid all the tedious work of finding the partial fractions. So here's the thing about partial fractions. They're very reliable in that they will always get the job done, at least in theory. And I'll talk about what I mean by in theory in just a moment. But although partial fractions are reliable, they're also a lot of work. And for that reason, I generally suggest using partial fractions as a last resort. So when you see a rational function, always look for easier methods first, but if you can't think of anything easier, then you can always brute force the job by using partial fractions. Now, let me clarify what I mean when I say partial fractions always get the job done in theory. In this example, we see another proper rational function, so we recognize partial fractions could get the job done. But what's the first step of partial fractions? Well, that would be factoring the denominator. But in this case, the denominator is 4th degree. It turns out that every polynomial of degree 3 or higher can be factored in one way or another, but sometimes it's really hard to figure out how to actually do it. So this is what I mean when I say partial fractions always work in theory. If you can't figure out how to factor the denominator, then you're kind of stuck. So in a situation like this, we'd have to put a significant amount of effort into factoring, so we need to find another way. And that's okay, because I just said before that I always suggest looking for another way before resorting to partial fractions anyway. So pause and see if you can figure out how to solve this integral for yourself, and when you're ready, let's look at the answer. As it turns out, this is yet another case where keeping the usual two things in mind will get you a long way. Those two things are the structure of f prime over f, or something similar, which might suggest some other type of nice u substitution. And the other thing is sums and differences of squares, which could suggest the use of inverse trig formulas. If you're looking for f prime over f, you'll notice we've got that if we just focus on the first term of our numerator. So that motivates us to split up our fraction, as we've seen quite a few times now. Well, the first term now is almost of the form f prime over f, but for that we would need to multiply and divide by 4. After doing that, though, we know the f prime over f integral becomes the natural log of the denominator with an absolute value. In this case, though, the absolute value isn't necessary because we know x to the 4 plus 1 is already a positive number. To deal with the second term, we notice the denominator here can be viewed as a sum of squares. To emphasize that, you could express x to the 4 as x squared squared. After doing that, we can more visibly see the structure of u squared plus a squared. With that, we can see that letting u equals x squared might be a good idea. So let's try it. In this case, du would be 2x dx. In the numerator here, we can at least see x dx, but it would be nice if we had a 2 here so that that entire chunk that I circled could just be called du. And I can have that 2 that I put there, provided I also cancel it out with a division by 2 in front. With that, you can go ahead and complete the substitution, and what remains now resembles our formula for arctan of u. So we can go ahead and apply that formula. Don't forget to put your final answer back in terms of x, and you're done. I'll reiterate that the purpose of this example and of this video is to again illustrate that partial fractions isn't always needed when dealing with rational functions. It's useful a lot of the times, but it's not always necessary. So in summary, always look for an easier way, and if you can't find one, that's when you resort to partial fractions. That's all I have for now, so I'll wrap things up here and see you next time.